Geometry of Dynamic Tetrahelix and Field Structures. This is part 1 of a lecture series on the geometry of dynamic tetrahelix and field structures. Physical models and a physics simulator will be used to explore the various properties and behavior of the tetrahelix and the potential relationship to field structures. Lecture Series Breakdown. Part 1, the basic structure and construction method of the tetrahelix will be described. Part 2, the introduction of the dynamic tetrahelix, which integrates movement into its structure, will be examined. Part 3a, the harmonic behavior of the dynamic tetrahelix, will be explored. Part 3b, the fractional harmonics within dynamic tetrahelix, will be explored. Part 4, the core field structure, CFS, which is a unique tetrahelix, will be examined as a model for field structures, and the modified tetrahelix system will be introduced. Part 5, the matrix of the modified tetrahelix system will be described. Part 6, the tetrahedral field structure, TFS, will be introduced and its potential use as a field structure model will be discussed. Tetrahelix basic element definition. A tetrahelix is defined as a sequence of face-connected tetrahedrons, or elements. One face of the tetrahedron is defined as an input face and an adjacent face is defined as an output face. This is used to define the direction of the tetrahelix. An arc shape can also be used as an element of the tetrahelix, which more clearly reveals its geometric properties and internal structure. Tetrahelix construction terminology. The first element of a tetrahelix is considered the oldest element. Subsequent elements are considered increasingly younger elements. The output face of older elements connects to the input face of the next younger element and establishes the direction of the tetrahelix. The younger elements can only rotate around the axis centered around the output face of the older element. Simple tetrahelix construction example. In this example, the tetrahelix is constructed one element at a time, and each new element is considered progressively younger. This establishes the direction of the tetrahelix. Tetrahelix rotation axes and angles. The bend angle is the angle between the input and output face of the tetrahedron, the dihedral angle. The twist angle defines the amount of rotation used at the face-to-face connections and is perpendicular to the output face. Each new element of the tetrahelix can be rotated with a step of the twist angle. The default is 120 degrees. A sequence of twist angles defines the tetrahelix as a sequence of digits. 0 indicates no step or rotation. 1 indicates a clockwise step of 120 degrees. 2 indicates a counterclockwise step of -120 degrees. Tetrahelix twist options. 2 indicates a left twist of -120 degrees. 0 indicates no twist. 1 indicates a right twist of 120 degrees. Arc element for the tetrahelix. A simple arc can be used as the element of a tetrahelix. This helps to reveal the internal structure of the tetrahelix and how its elements interact with each other. This is a left twist. This is no twist, and this is a right twist. Tetrahedral Arc Definition. The arc is created from the intersection of a torus and a tetrahedron. The torus is centered at the midpoint of an edge of the tetrahedron and passes through the center of its adjacent faces. The arc shape still retains the essence of the tetrahedron used in the classical tetrahelix. Tetrahelix construction examples. Tetrahelix are defined as a sequence of digits, 0, 1 and 2, that represent the twist angle used for each element. A subsequence is used to describe a tetrahelix and its total length is defined in multiples of the subsequence length. Here are a few examples for a tetrahelix, with the 3-bit subsequence of 010, 011 and 221. The first, or oldest element is fixed in world space. Then a subsequence of 020 is defined and saved. In this example, the tetrahelix is built with a length of 24 elements. The elements can then be changed to an arc, and the subsequence is redefined and the tetrahelix can be rebuilt. The arcs reveal more clearly the internal structure of the tetrahelix. Tetrahelix Classifications. There are generally three main classes of tetrahelix. Linear tetrahelix, twist along a primarily straight path. Spiral tetrahelix, twist along a spiraling path. Loop tetrahelix, twist along a circular path. Here are a few examples of a linear tetrahelix. Below each image is the associated subsequence that was used to construct it. The length of the tetrahelix can be defined in the simulator. Here are a few examples of spiral tetrahelix. Below each image is the associated subsequence that was used to construct it. The length of the tetrahelix can be defined in the simulator. Here are a few examples of a loop tetrahelix and the associated subsequence that was used to construct it. The length of the tetrahelix can be defined in the simulator, but there will be a gap in the loop if the length is too short. Or the elements will overlap if the length is too long. Loop tetrahelix. The primary focus in the rest of the presentation will be on the loop tetrahelix, which almost form closed loop circuits. The elements in the loop tetrahelix do not perfectly align, so there will be a gap between its oldest and youngest elements. However, I have found a simple way to close these gaps and create closed loop circuits. This will be examined more closely in Part 2 of the presentation. Part 2, the introduction of the dynamic tetrahelix, which integrates movement into the structure, will be examined.